All right, welcome to The Explainer. Today, we are going to dive right in. And I mean that literally. We're taking a journey from the beaches we all know and love, all the way down into this completely hidden, almost alien world at the bottom of the sea. So, let's get going. So, let's just kick things off with a fact that's going to totally flip how you see the world. You know the highest mountains on the planet? The Alps, the Himalayas? Well, the rock that makes them up, it was once mud and sand at the bottom of the ocean. Just think about that for a second. It's this incredible reminder that the deep sea is literally responsible for the ground we walk on. And suddenly, that starts to make a whole lot more sense when you remember that, well, almost 3/4 of our entire planet is covered by water. And we're not talking about paddling pools here. A whopping 80% of that ocean is over 3,000 meters deep. It is just a vast, mysterious, and incredibly powerful place. Okay, so our journey starts somewhere we've all probably been, the coast. This is where we see the ocean's power up close, right? It's this zone of just constant, restless energy, where the sea is literally carving and shaping the land day in and day out. So, have you ever actually stopped to think about how a wave works? It's pretty cool. Way out in the deep ocean, a wave is just energy, moving through the water in these big circles. But as it gets closer to the shore, the bottom of that circle starts to drag on the seafloor. That friction slows everything down, pushes the wave up taller and taller, until it just can't hold its shape anymore, and bam, it breaks, and all that energy gets dumped right onto the beach. Now, here's the thing. Waves almost never come in perfectly straight. And that little angle, it's the key to everything. It creates one of the most important processes on any coastline, something called longshore drift. The best way to think about it is like a river of sand, just constantly flowing along the edge of the beach. And you can picture exactly how it works, right? A wave comes in, pushes a bunch of sand up the beach at an angle, but then gravity just pulls it straight back down towards the water. So you get this constant zigzag, zigzag, zigzag motion. Multiply that by thousands of waves every single day, and you're moving incredible amounts of sand down the coast. It's constantly building up one beach while, you guessed it, stealing sand from another. And all that energy, it's not just moving sand around. Oh no, it's powerful enough to demolish solid rock. Imagine the waves just hammering away at the base of a headland, carving out a little notch. Eventually, the rock on top can't support itself and it collapses, leaving a steep cliff. And then, over thousands of years, as that cliff slowly gets eaten away and retreats, it leaves behind this flat, rocky shelf called a wave-cut platform. All right, so we've seen what happens at the edge. Now it's time to head offshore. We're going to start our descent down the real edge of the continent and plunge into the deep. So this trip down, it's not just one big slide. Think of it more like a series of steps. First, you've got the continental shelf, which is this pretty broad, gentle platform that stretches out from the coast. Then you get to the edge of that, the shelf break, and suddenly, whoosh, you're dropping down the much steeper continental slope. At the bottom of that, things start to flatten out into what's called the continental rise, and that eventually just melts into the abyssal plain, which is, no joke, one of the flattest places on the entire planet. But wait a second, how does it get so flat? The answer is, well, it's pretty wild. It's basically underwater avalanches. They're called turbidity currents, and they are just this chaotic, super fast-moving mix of mud, sand, and water. It gets so dense, denser than the water around it, that it just comes roaring down the continental slope, all thanks to gravity. And we are not talking about some gentle little mudslide here. These things are so powerful they can carve out gigantic submarine canyons. Some of them are way bigger than the Grand Canyon. And when one of these currents finally runs out of steam on the deep ocean floor, it just dumps its entire massive load of sediment. And this stuff spreads out in these huge sheets. They're called turbidites. And they basically pave over everything, burying all the hills and valleys and creating that perfectly smooth, billiard table flat surface of the abyssal plain. Okay, we've made it. We're at the bottom. We're talking depths of over 4,000 meters here. This is a world of absolutely crushing pressure. Total, complete darkness, and a landscape that is just, well, it's completely alien. But flat doesn't mean boring or featureless. Not at all. The abyssal plains are dotted with hills and huge underwater volcanoes called seamounts. And get this, snaking its way across the entire globe is the mid-oceanic ridge. It's a continuous chain of volcanic mountains that stretches for 64,000 kilometers.
It is by far the single largest geological feature on our planet. And of course, you got the trenches, the absolute deepest spots you can find anywhere.
You know, the chemistry down here in this deep, dark world is just totally different from the surface. Without any sunlight, there's no photosynthesis, so the CO2 levels just skyrocket. In fact, the deep ocean water is way richer in carbon dioxide than the air we're breathing right now, and all that extra CO2 makes the water more acidic.
And that acidity creates this really interesting chemical tipping point. It's called the calcite compensation depth, or the CCD for short. Think of it like an invisible line in the ocean. If you're above that line, the little calcium carbonate shells of tiny sea creatures can survive and fall to the seafloor. But if you're below it, the water is so corrosive that those same shells just dissolve. They literally vanish into nothing.
So as you can imagine, this completely changes what the seafloor is made of. Just above that invisible CCD line, the bottom is covered in this thick, chalky mud made from zillions of those tiny calcium shells. It's called a calcareous ooze. But once you drop below the CCD, all that stuff is gone. Only the tougher, silica-based skeletons of other little organisms can survive, and they form something called a siliceous ooze. And if you go to the very deepest parts of the ocean, even the silica dissolves. All that's left is the stuff the water just can't break down. And that final sediment, it's called red clay. And it's made of the most amazing stuff. It's the finest dust from volcanoes and deserts that is drifted out to sea. It's cosmic dust that's rained down from space. And it's the toughest biological bits that just won't dissolve, like shark teeth and the ear bones of whales. And it builds up at this unbelievably slow rate. We're talking maybe a centimeter every 1,000 years. It is literally a museum of ancient history, just sitting there on the bottom of the ocean. Okay, so let's zoom back out. Let's bring it all the way back up to the surface. How do all these huge, slow-motion, deep-sea processes, how do they connect back to that restless coastline where we all live?
Well, here's the connection, and it's a big one. Remember that giant 64,000-kilometer-long mid-oceanic ridge? The sheer volume of that mountain range displaces a mind-boggling amount of water. In fact, if that ridge system just wasn't there, scientists estimate that global sea levels would be about 300 meters lower than they are now. That's an incredible reminder that what happens in the deep really does decide where our coastlines are today.
And up on those coastlines, we're in this constant battle, right? We're fighting against the very forces we talked about at the beginning. To stop erosion, to try and control that river of sand from the longshore drift, we build these massive structures. You've seen them. Jetties, breakwaters, seawalls, groins, all of them are designed to try and hold the land still.
But there's always a but. There's this unavoidable trade-off. Let's say you build a groin to trap sand and make your beach bigger. Well, you've just put a dam in that river of sand. Sure, your beach gets wider, but you've just cut off the supply for the beach downstream. You've starved it of sand. And that means the erosion there is going to get way, way worse. See, you don't actually stop the process, you just push the problem down the coast for someone else to deal with. And that brings us to the big final question, doesn't it? We've gone from the crushing depths all the way to the restless shore, and the one constant is that the ocean is this place of immense, relentless power. So as our world keeps changing and sea levels continue to shift, what's our move? Do we keep building bigger and bigger walls to try and fight that power? Or do we need to start getting smarter about how we adapt and learn to live with it?